This video, we're going to take a look at the orbitals and the electronic structure of the atom in greater detail than what we've talked about before. Specifically, we're going to draw what are called orbital energy diagrams. Now, these drawings are not going to be the same as the drawings of the orbitals themselves, far from it. In fact, these are going to be very simplified, stylized views of the orbitals and their relative energies. The focus here is on the energies of the electrons, not specifically the shapes of the orbitals themselves. The reason for that is that in chemistry, energy is all important. It's the most important thing. In fact, all of chemistry can boil down to simply the idea that electrons are trying to find an atom where they can be closer to the nucleus, to the positive charge at the center of the atom, by which we can also use as a proxy for that measure, having a lower energy level or inhabiting an orbital, a lower energy orbital in a lower energy level. So we're going to see the electrons spend their time just trying to find the lowest energy levels. But those spaces are limited, and we'll see how limited they are. The closest orbital, the lowest energy orbital is in a given energy level is the S-type orbital. And there are only 2 electrons allowed in the lowest level S-type orbital. So getting a seat sort of at, up near the nucleus is sort of like trying to find a front row seat to a very popular music concert or something like that, where there are very limited seats, but a lot of people want them. All electrons want to be near the nucleus, but there are only 2 seats available at the front row. But as you go further back, there are more available energy slots, or in our analogy, that would mean more seats in the back. So let's take a look, and we can see this pictorially by drawing what are called orbital energy diagrams. Again, these are not the drawings of the orbitals, though we will start off by just reviewing the different types of orbitals. So just to recap what we talked about in our previous video, electrons don't just randomly live around the nucleus in an atom. We say there's an electron cloud around the nucleus, but this cloud has shape and has structure, even if the structure isn't a physical structure, and even if the borders aren't real, just like the borders on a map are not real. Nevertheless, there are defined, mathematically defined areas in which you can find electrons. So electrons inhabit defined volumes of space at specific energies around the nucleus. The further away from the nucleus the energy goes, on average, the higher energy that electron is. Of course, just recapping the history of atomic models, in the early 20th century, scientists imagined that electrons orbited the nucleus like planets around the sun. Now, we know that's not true anymore. However, that is still a useful picture in some ways. And we will actually return to that outmoded and outdated view of the atom, because though it's not perfectly accurate, it does encapsulate the most important aspect of electrons in their orbitals, which is that they are at different energy levels. It's all about the energy and the distance from the nucleus. So the further away an electron or its orbit takes it from the nucleus, the higher its energy level. Far enough away from the nucleus, and you can consider the electron to have left the nucleus altogether. This is referred to as ionization. Ionization. Ionization is the removal of an electron completely from an atom. But the removal of an electron from an atom simply entails taking that electron and moving it beyond a certain threshold distance away from the nucleus. In essence, even if you moved an electron to the other side of the universe, of the atom that it once inhabited, you could, in theory, you could realistically say that the electron is simply inhabiting an extremely high energy level. Now, for practical purposes, that doesn't make a lot of sense. But mathematically, the energy levels do continue on for infinity. But for our purposes, we're going to represent the energy levels only through level 7, which is the number of rows of the periodic table. And we will see in this video how the rows of the periodic table relate to the energy levels. Of course, today the picture of the electron in atoms is more complex, but it still includes different energy levels. So in that respect, it still makes sense to talk about the old planetary model. In fact, we will return to that in a very near-term future video when we talk about the interaction of light and electrons, excitations and relaxations of electrons, or electron transitions. The fact that the electrons don't orbit in circles, but they inhabit orbitals, doesn't impact the central premise that energy is exchanged and energy is involved in the placement of electrons around the nucleus. Okay. So different energy levels have different possible orbitals within them. Now, we haven't spoken about this before. It sounds like I'm saying the same thing, but I'm not. Different energy levels have different possible orbitals within them. At energy level 1, which pictorially is represented in the periodic table itself, you have only one kind of orbital, and that is the S-type orbital. At energy level 1, you correspond on the periodic table to row 1. Of the periodic table. Row 1 of the periodic table has only 2 elements, hydrogen and helium, and they are both part of the so-called S block. Energy level 2 has 2 different kinds of S orbitals, 2 different types of orbitals, S orbitals and P orbitals. When you go to row 2 of the periodic table, you can see this because the left-hand side of the periodic table contains the S block elements, lithium and beryllium. And on the right-hand side, on that same row, level 2, which also corresponds to the energy level 2, row 2, contains 6 P block elements from boron to neon, boron to neon. Those are P orbital elements. So there are P-type orbitals and there are S-type orbitals in energy level 2 or row 2 of the periodic table. Energy level 3 has 3 kinds of orbitals. Now we've added to the S and the P, now we add D, and then finally energy level 4 and onward have all 4 kinds of, or all 4 types of orbitals, S, P, D, and F. Every energy level you go up, you increase, you add another type of possible orbital that exists at that energy level. The more energy, in other words, the further away the electrons are from the nucleus, the higher energy they are. The higher the energy, the more the different possible arrangements or orbitals of the electrons, the more ways the electrons can find to exist and orbit or inhabit orbits around orbitals around the nucleus. More energy just means more possibilities, more different configurations of the way electrons inhabit the nucleus. For the main group elements, the S block and the P block elements, the energy level is the same exact numerical value as the row number. So energy level 1 corresponds to row 1. Energy level 2 corresponds to row 2, and so on. In fact, we'll see that very soon when we look at the periodic table, because we're going to use the periodic table as our guide to drawing orbital energy diagrams. Okay, again, to recap, these are the lowest energy representations of all the different types of of the 3 types of orbitals, S orbitals, P orbitals, and D orbitals. I didn't represent the F orbitals. Their shapes are a little bit more complicated. For our purposes, we're not really going to delve into their shapes or their names. Just remember there are 7 F-type orbitals, and that's all we really need to remember. Remember that there was only one kind of S-type orbital, a sphere. It's the simplest and lowest energy orbital. And the reason it's simplest and lowest energy is because it's a sphere. A sphere is not a complex shape. Complexity in nature is associated with high energy. A non-complex shape like a sphere, which is the same in all directions, or isomorphic or isotropic, meaning it's the same in all directions, it doesn't change, makes it a rather simple orbit, or orbital, I should say. This is a sphere, not a circle, by the way. So a simple, low energy will have just enough energy to create a simple type of orbital. But as you gain energy, you have more complex arrangements like these p orbitals. So we have an S-type orbital. There's only one S-type orbital. We've talked about this before if you've seen an earlier video. There's only one type of S orbital. There is no subshell for the S orbital. A single orbital doesn't make a subshell. However, there is such a thing as a subshell, or sometimes referred to as a sublevel, for the p orbitals because there is a set of 3 different orbitals. And we took a look at their orientations. They're all the same shape, but they have different orientations around these axes, px, py, and pz, in no particular order. There is no preferred order, and there is no preferred Cartesian system. So a set of 3, this is the p subshell, 3 orbitals. These are 3 separate orbitals in one set or one subshell. 3 separate orbitals. 3 set orbitals. Set of 3 orbitals. And then we have the d orbitals. And we have a set of 5 discrete or distinct orbitals making up the d subshell. And then, of course, there's the f subshell. There are 7 f orbitals in the f subshell, which we're not going to represent. Don't worry about the shape. We're not going to really talk about it. 7 f orbitals in the f subshell. 1, 3, 5, 7. They're always going to be odd numbers. If there were a G sublevel or subshell, it would have 9 orbitals. So these are the pictures of the orbitals. We are not going to draw orbitals. We're not going to spend our time. I do want you to be able to draw the orbitals and remember their pictures, but because that's going to come in handy further down the line in your chemistry journey, but not right now. So I do want you to recognize the orbitals when you see them, but we are not going to spend our time drawing these elaborate shapes and pictures, especially when they overlap. They're going to be impossible to understand. Remember, every one of these orbitals overlaps each other. I'll show you what I mean. For example, you don't just have the s orbital. You have the 2d orbital. You have all 3 2d orbitals, px, py, pz. Then you have all the d orbitals, which I'll represent with a different color. Then you have all your d orbitals, all 5 of those. And to a certain extent, they all overlap. So imagine trying to make sense of a diagram like this, where you have all these overlapping orbitals all centered around the same nucleus. It's a mess. So we don't draw this. We don't waste our time drawing the actual physical picture of the shapes of the orbitals because it would be incomprehensible to anybody. We don't draw that. Instead, we represent orbitals as simple graphics. We represent them this way. We represent an orbital as simply a line, and we're going to go into this in more detail in the upcoming slides. We represent an orbital either as a line or, if you prefer, and this is certainly an option if you like it, or a box. That's an orbital, and the way you know the difference between one orbital and another is simply to label it 1s or 2p or 3d or 4f, whatever you want to call it. Or maybe a 3s orbital, or a 5p orbital, or a 6f orbital. Wait, is there a 6f orbital? There are no 6f orbitals. I went a little too far there. Not yet, anyway. 6d orbital, etc. So you can simply label these. You don't really need, you simply draw a line or a box, you label them, and then you put electrons in them, which we'll represent as half arrows, up or down. And I'll explain the up or down in a future video. So that's how we're going to label these orbitals. We are not going to draw them out because that is just impractical and virtually impossible to understand for anybody. So we're going to draw orbital energy diagrams. Specifically, we're going to draw ground state orbital energy diagrams. The ground state refers to the lowest possible energy configuration of all the electrons, meaning none of the electrons are in higher orbitals, higher energy orbitals than they absolutely must be. They're in the lowest possible energy orbitals. No low energy or low lying orbitals are left empty, while higher energy orbitals are filled. That's what a ground state means. The opposite of the ground state is the excited state. So here I just described what I just did. We're going to represent orbitals as lines and electrons as arrows. The only thing we're going to need to know for every one of these orbitals is the energy level n. Remember, n was called the principal quantum number, also designated as letter n. Principal quantum number. Most of the time, we're just going to refer to it as energy level. The energy level n, which is again a number from 1 to 7, and the type of orbital, s, p, d, or f. And when you put those together, you get n, s, n, p, n, d, n, f. Now, at energy level 1, you have only one kind of orbital, s-type orbitals. And you have absolutely there is no such thing as a p-type orbital. Remember, at energy level 1, there's only one type of orbital available. Now, if you forget that, just go back and review this, what we just talked about. Review that slide, because that's an important thing to remember. Energy level 1 has only one kind of orbital, and that is the s orbital. That is it. You'll see this again and again in the periodic table. In fact, every time you look at the periodic table, it's a reminder of these kinds of rules. Then we have energy level 2. At energy level 2, we have a 2s orbital. We also have a 2p orbital. At energy level 2, we have two kinds of orbitals available, s-type and p-type. However, we still do not have any kind of d orbitals or f orbitals. So these are still out. Then we get to energy level 3. Then we have three different kinds of orbitals available. We have the s, we have the p, and now we have a d-type orbital available to us. But again, no f-type. Every time you go up one energy level, you add another type of orbital that is possible at that energy level. Finally, once you get to row 4 and anything higher, all available energy levels or all energy levels are possible, well, until we come up with elements that have g orbitals, but we don't have any of those yet. 4s, 4p, 4d, and 4f. And then it goes on, 5s, 5p, 5d, 5f. That's the limit of f. We'll see later why that is, but the s's and p's go all the way down to the very bottom of the periodic table. So this is how we are going to label every one of our orbitals. We're going to label them like this: 1s, 2s, 2p, 3s, 3p, and so on. And we're going to follow the periodic table so that we're going to go from 1s to 1p to 2p to 3s to 3p. And you've probably seen something like this. I'm not exactly sure how it goes. I've never used this sort of scheme before. 3p, 4s, 3d, 4p, and then 5s, 4d, 5p, and so on. Sort of a zigzag route. Doing it this way, I do not recommend looking at it this way. Use the periodic table. It's far easier to understand. Speaking of the periodic table, here it is. So this is the periodic table layout by block. Remember, we learned about the blocks of the periodic table, the S block, the D block, the P block, and the F block. So we're going to use these blocks. I'm going to give you a little preview right now, but we'll get into the details in a bit. But remember that, first of all, remember that helium was, while normally over here, it's been moved over here. So this is helium. I moved it to be with its fellow block members. That doesn't mean you should do that on your regular periodic table, unless it helps you. If you want to, go ahead. But I moved it over here because helium is technically a part of the S block. The S block are is comprised of the first two columns of the periodic table, the S block. Over here, we have both the row of the periodic table, 1 through 7, and we have, but what I've labeled this over here as is energy level N, the principal quantum number. Now notice, 1, 2, 3, 4, 5, 6, 7, the row of the periodic table corresponds perfectly to the energy level of the S and the P orbitals. However, there is a mismatch for the D and the F orbitals, as I've noted here on the side. Once we get down to where there are D block elements and F block elements, there's a slight mismatch, a slight offset, and we'll get to that. We'll talk about that in a future video. For this video, I want to keep it, this video is part 1 of 2 different videos. I'm going to keep it simple and stick to the main group elements for this video. And cover some of the basics of ground state orbital energy diagrams and what are called electron configurations. So how do we label these? Well, for the first element, the very first element, hydrogen, we have energy level 1. So that's going to be a 1. We always label starting with the numerical value of the energy level, and we indicate the type of orbital, which corresponds to the type of orbital that element is in, whichever block it's in. It's in the S block, so it's 1s. For helium, it's still in row 1. Remember, even whether you put helium over here or you put helium over here, it's still in row 1. So helium is also 1s. The single orbital in helium is 1s. That's it for row 1. There are only 2 elements in row 1. Once you go from left to right and then from one row to the next. So once you finish one row, you go to the next row. How about 2? Well, here we have lithium. If you're following along with your periodic table, I certainly hope you bring your periodic table or have your periodic table with you every single time. Lithium has 3 electrons. We're going to go into this in more detail. I don't mean to cover this. I'm not trying to cover this very thoroughly right now, but I just want to introduce the topic. We are now at row 2. So lithium is going to have as its highest energy orbital 2, energy level 2, but it's still in the S block, so 2s. That's its highest energy orbital. However, lithium contains all the electrons and all the orbitals of all the elements that preceded it, that came before it. So not only does lithium have the 2s orbital with a single electron in it, but it has the 1s orbital with 2 electrons in it. The core of lithium, we say, looks just like helium, the core, the inner electron. All right, so I just wanted to show this to you. So the way you would label all of this is you label them 2s, 2p, 2p. Notice as we come across to the p block, we are still on row 2. So this is still 2, 2, 2, 2. The only difference is now we are in the p block. These are p orbitals over here, p orbitals. Then we go to row 3. 3, 3, but then we're in the S block, so we label our orbitals S. Then we jump over to the P block, where we label our orbitals P. But again, we have not left the row. Remember, a row is a horizontal, from left to right, a horizontal arrangement. A row is flat. So we have not left row 3. Simply jumping across to the other side of the row doesn't change rows. We are still at row 3. Row 1, row 2, row 3. So this is 3p, 3p. All of these elements contain 3p electrons, meaning electrons inhabiting 3p orbitals. Then we get down to row 4, 4s, 4s, 4p, 4p. Remember, for the S and the P block, the row number of the periodic table exactly corresponds to the energy level of the orbitals. This is an incredible coincidence, and it's only a coincidence. The periodic table was not laid out according to orbital energies. There was nothing even known about orbital energies when the periodic table was invented. They were not even totally sure atoms existed when the periodic table was invented, let alone the existence of electrons. They would have no idea what an electron was, or a proton, or anything else. So this was quite an achievement. It's quite amazing that the periodic table ended up being so congruent to and corresponded to all the energies of these subatomic particles. However, it's not perfect. So like I indicate here, 3D, the D block actually lags behind the row number it's on. So instead of being 4D, it's 3. You always take the row minus 1. Actually, let me write that over here. The rule is, generally speaking, to do this. Take the row number, subtract 1, and that equals the energy level of the D block. That's the energy level of the D block. Or I should say the D orbitals. For any given D subshell or D orbitals, it's the row number that you're on. So what row are we on? 1, 2, 3. We are on row 4. We are on row 4. Remember, moving left to right across a row does not change what row you're on. We're still on row 4. However, the row minus 1, that's 4 minus 1 equals 3D. So this is 3D. So all of these transitional metals have 3D electrons inhabiting 3D orbitals all the way across. The next D level, the next row of D orbitals are 4D. Why? Because we're at row 5. Row 5 minus 1 equals 4D. 4D all the way across. 4D. And then you're back up to 5P again. So again, for the S and P blocks, the row number of the periodic table always exactly corresponds to the energy level N. However, for the D block, the energy level lags behind by 1 integer number. So it's the row number minus 1 is the energy level N of the D block. For the F block, it's the row number minus 2. Row number minus 2 equals the F orbitals. So N equals that. So for example, when we're at row 6, and remember the F block is part of the periodic table. These are actually rows 6 and 7. At row 6, 6 minus 2 equals 4F. 4F, all the way across. And likewise, at row 7, 7 minus 2 equals 5F. So the highest energy F orbital that's available so far, given the elements that we know of, is energy level 5. So the D orbitals and the F orbitals are simply, you could say they're misplaced in the periodic table. That's because the periodic table is arranged in ascending order of atomic number. And by arranging it that way, it puts the D block elements on the 4th row rather than the 3rd row. And likewise, it puts the F block elements on the 6th row rather than the 4th row. That's simply the way it goes. But if you look at the atomic numbers, they do increase sequentially. So if you look at, for example, the elements, the atomic numbers here on the 4th row, you have element number 19, 20, and then scandium, our very first transitional metal or D block element, is element number 21. If we were to have moved the D block 1 row up, we would have been out of order. And you know, it's a judgment call how you want to arrange the periodic table. Atomic number seems to be the preferred way to organize the periodic table rather than on the basis of orbitals. So 19, 20, 21, the order of the increasing or ascending order of atomic number was preserved, but of course, energy levels are now sort of offset. So these 4th row or fourth period d block elements have 3D or have energy level of 3. They are 3D orbitals, and so on, 3D, 4D, 5D, 6D. Notice that the highest energy d orbital that's possible is only 6D. It doesn't go all the way up to 7. The highest energy s-type orbital available is 7s, and the highest energy p-type orbital is 7p. But d elements only go up to 6D, f elements only go up to 5f. Again, p block and s block increase all the way. So that's the layout. You have your S block, you have your D block, which is one integer number lagging behind the row number in terms of energy level. You have your P block, and you have your F block, which is 2 integers or 2 numbers or 2 units less than the row number for its energy level, for its corresponding energy level. Okay, we're going to get plenty of practice with this. This is not how you draw an orbital energy diagram. I just wanted to introduce the topic. So relative orbital energies. We are not going to deal with absolute energies here. While that is a possibility, that is not something that's generally helpful for us. And the calculation of those things goes back to solving the Schrodinger equation, which of course we're not going to even attempt to do here. So we're simply going to compare energies qualitatively. We just want to know which orbitals are higher in energy than others. And there are some very simple and predictable and consistent rules about which energy levels are higher than others for the most part. Orbitals are drawn, okay, let's just talk about how we draw orbitals. I mentioned this already, I'll mention it again, I'm going to keep mentioning it. Orbitals are drawn simply as short lines. So you draw it like that with their energy level and their orbital label beneath the line. So for example, if I wanted to represent the orbital 4DZ, or so let's say 4DXY, I would simply label this line as 4DXY. This would represent a d orbital, specifically the dxy orbital, and that the level energy level 4, n equals 4 type of orbital is d type. And specifically in that subshell, it would be the d type orbital that is sitting in between the x and the y axes. So you have your x-axis, you have your y-axis, and then you have your d-type orbital. But rather than drawing this type of orbital, remember, we're not going to draw these pictures. I'm just showing you this so I can cross it out and tell you we don't have to do that. Instead, all of that information is right here in this simple little label and line. That's it. And if I want to represent this orbital with electrons inside of it, I simply draw 1 or 2 electrons. The maximum number of electrons is 2. We can never have any orbital, no matter the size or energy level, no orbital will ever have more than 2 electrons inhabiting it. You can have 1 electron, you can have an empty orbital with 0 electrons, but you can never have more than 2. Electrons are represented as vertical arrows pointing either up or down. So here they are. And you can see I drew them that way over here too, up or down. I'll explain later why that is, why they have direction. It has something to do with the magnetic field generated by a spinning negative charge or a spinning charged particle. Orbitals are drawn in vertical arrangement. Now this is a critical piece of information here. The reason it's so critical is because there's really no use in drawing orbital energy diagrams if you don't represent the actual relative energies of the orbitals. You may as well just draw yourself an electron configuration for the most part, which is a simplified and much less detailed version of method of representing electrons in their orbitals. So they are drawn in a vertical arrangement with respect to one another in order to graphically represent or present their relative energies. The higher the energy of an orbital, the further up, the greater the height at which you plot or you draw that orbital's line in its label. You're not going to have to plot anything. There are no functions here to plot. You simply place them higher up physically, geometrically, you place them higher up on your page than the lower energy orbitals. There are two energies to consider when comparing orbitals. Luckily, these are totally predictable rules, and they do not really vary for the most part. Number one, the main thing is to compare energy levels. For any orbital, if you're looking at the energy levels, the higher the n value, the higher the energy. It doesn't matter what type of orbitals you're comparing. If you're comparing an S-type orbital to a D-type orbital, and the S-type orbital has a bigger n value, has a higher energy level, it's the higher energy orbital. A 5s orbital is higher in energy than a 4d orbital. A 7p orbital is higher in energy than a 6f orbital. Again, there's no such thing as a 5f orbital. A 5f orbital. The first consideration is the energy level. If the energy level is larger, if the n value is bigger, then that orbital is higher in energy. Now, if you're considering two orbitals of the same energy level, so if the energy levels are equal, then you move on to comparing the orbitals themselves, and the order is always the same. The s orbitals are always for a given energy level, meaning assuming that all the energy levels for all these orbitals that we're comparing are the same, s is the least energetic orbital. It's the simplest and lowest energy, most stable orbital. S is the lowest energy, F, as in Frank, is the highest energy. So it goes from S, lowest, P is the next lowest, D is the second highest, and F is the highest energy. It's in that order, but again, only if you're comparing like energy levels. If the energy levels are different, then you know which orbital is the highest energy. It's the one with the biggest n value, the biggest principal quantum number n. So again, 5s beats 4p or 4d or 4f, because even though s-type orbitals are the lowest energy, the higher energy level, the lowest energy of the highest energy level is the highest energy orbital. I'll say that again, slower. The lowest energy orbital of the highest energy level in a comparison is the highest energy orbital. Being at the bottom of the next highest level still puts you on top of everyone who's in the lower levels, right? That's what it means. Or put it more realistically, the poorest member of Jeff Bezos's family is still way richer than everybody else. Think about it that way. The poorest rich person is still richer than you. I'm guessing anyway, certainly richer than me. So even if you're at the bottom of the very top level, you're still above everybody else. That's how orbitals work. That's kind of a crass economic metaphor, but I think it's apt. Sets of orbitals that have the same energy are called degenerate. We're going to see this word again and again, degenerate. The most common examples are the p subshell and the d subshell. Orbitals of the same subshell are always degenerate, meaning they always have the same energy. All the 3p orbitals, remember or 4p orbitals, or the 5p orbitals, or the 2p orbitals, all the p orbitals in a subshell, a p subshell, have the same energy. One is not higher in energy than the other. So they are all degenerate. In other words, their relative energies with respect to one another are the same. What are the energies? Happily, it doesn't matter to us. We don't care about absolute values or absolute numbers here. We just care about relative position. So the 3p orbitals The 3 different p orbitals in a p subshell are all degenerate. They're all the same energy. This is an important concept because some of the rules, or one of the rules, with reference to how you put electrons in orbitals, makes specific reference to degenerate sets of orbitals, meaning orbitals that are equal in energy to each other within an atom. So we're going to put all of this together, and you're going to understand. Right now, this is all very abstract, probably, but we're going to put all of this together when we actually walk through a bunch of examples soon. But I'm just laying the groundwork right now. But when we do the examples, think back to this and even go back and read all this stuff again and redo the examples on your own, and you'll see how every one of these things applies to what we're going to do when we actually draw the orbital energy diagrams. I promise you we're getting there. Valence and core electrons. The highest energy electrons. This is one of the main reasons you want to know about the relative energy levels, because you want to be able to spot valence electrons. Valence electrons do all the work in an atom. They're responsible for all the chemical reactivity. Valence electrons are responsible for the positive charge of ions, of positively charged ionic atoms or cations. They're also responsible for the negative charge of anions in the sense that electrons gained by an atom are put into valence or formerly empty valence or half-filled valence orbitals as well. So the valence electrons are the electrons that do all the work in chemistry. The core electrons do virtually nothing. In fact, core electrons are as fixed and integrated and as much a permanent, unmovable fixture of an atom as almost as the protons and neutrons are in the nucleus. Core electrons are virtually never lost except under extreme high energy conditions that frankly are not the norm in chemistry. So core electrons are pretty much fixed, almost as fixed as the protons are, in the sense that it takes an incredible amount of energy to remove them, and that doesn't generally happen. So core electrons stay put with the atom that they were in, but valence electrons, they move. They can be transferred. They can either be gained or lost by various atoms. When we talk about electrons being gained or lost by atoms, we are talking almost exclusively about the valence orbitals and the valence electrons that are in those orbitals or that are going to inhabit those orbitals. And those are the highest energy electrons. Think of it this way, the highest energy electrons are also the least stable. They are the least happy where they are, because again, high energy implies they are far from the nucleus. And electrons, being negatively charged, want to be near all that concentrated positive charge at the center of the atom, but they can't be because there are limited seats. There are only 2 electrons allowed in the lowest energy level and the lowest energy orbital of any atom anywhere. The interior electrons are the core electrons. They're referred to as core electrons. They are almost as permanently attached to the atom as the protons. Okay, so which ones or what are the valence electrons? Again, these are very predictable and consistent rules. And this is how you'll always be able to recognize valence electrons by these, for these particular types of elements. S block. The S block elements, meaning any element in the first 2 columns of the periodic table, and also, of course, helium, any S block element has its valence electrons as the highest energy S orbital electrons. So any S block element will have the highest energy, not just any S orbital, but the highest energy S orbital. So say, for example, say something like potassium. Take potassium as an example. Potassium, you have the potassium atom. It has 1 S orbital electrons, it has 2 S orbital electrons, and it has 3 S, and it even has 4 S, if I remember my periodic table correctly, which I hope I do. I believe, potassium is on the 4th energy level and the 4th row of the periodic table. So it has 4 different S orbitals. However, only the electron in the last S orbital, only this electron, its single electron here, is valence, meaning the highest energy electron. The other 3 are core. They are core electrons, and they remain fixed in position. They do not leave the atom. These are core electrons. So when I say s block elements have s orbital valence electrons, I don't mean just any s orbital. I mean only the highest energy, and that's always the case. Only the highest energy of these types of orbitals can be valence orbitals, meaning holding the highest energy, holding the electrons that can be gained or lost. If the orbital is empty or half filled, meaning it doesn't have its full capacity of electrons, it can take on more electrons. If it's giving away electrons, the electrons in those valence orbitals will be lost, creating positive charged ions. Of course, potassium has other types of orbitals other than s-type orbitals, but I just wanted to make the point that it's only the highest energy, the 4 here, not the 1, 2, or 3s orbitals, that are that's the valence electron, valence orbital. And that electron in that orbital is your valence electron, only the highest. P block elements have both s and p orbitals. So P block elements can lose, or can think of it as losing, but you can also think of it as gaining. But P block elements can exchange or share both their P type or their P orbital electrons and their S orbital electrons. They can share both, or they can deal with both. They can do chemistry with both of those. But again, they have to be the highest energy level of those particular orbitals. D block, D only shares or only deals with S and D orbital electrons, only S and D, the D block. Notice that each block ends with the element in each block has valence electrons that end, or its valence electrons involve the orbitals that are named after that block. So a D block element will involve both S and D. A P block element will involve both S and P. An S block element will involve only S. So for a given energy level and for a given element, its highest energy orbital and all the ones preceding that highest energy orbital, but still within the same energy level or close to it, will be valence. Now, you might wonder, didn't you say earlier that D was a lower energy level? Yes, I did. So for example, for an element like, say, for example, iron, which is in the middle of the 4th row, it's a D block element. So its valence electrons are going to be the 4s electrons, the two electrons that are 4s, the superscript here represents electrons, the 4s is the orbital, and the 3d6 valence electrons. If you count the number of electrons from scandium, titanium, vanadium, chromium, manganese, or maybe the other way around, and then finally iron, when you count the number of d orbitals or boxes in the d block to iron, you'll see that you have 6 electrons. So it's 6 plus 2 equals 8 valence electrons. So when it comes to the D block elements, you actually have part of the valence electrons are the highest energy orbitals of the previous energy level. So it's the very top of the next lowest level. And for the F block is actually a little bit unusual. The valence electrons for the F block are the S and D orbitals. Again, you might ask, well, what about the F orbitals? The F orbitals may or may not be involved. It's actually not very predictable. Different F block elements will have different sort of valencies, meaning they'll give up different energy level electrons. It's not a predictable rule. I recommend that if you really want to know a particular F block element's electron orbital energy diagram or its valence electrons or what's called its electron configuration, I recommend you simply look it up. There are no rules that are really worth memorizing for the F block. It's not the sort of thing that you can really rely on. It's something you're just going to have to look up. When you need it, look it up. You have my blessing with that. Look it up if you need an F block element's valencies. So don't worry about the F block too much. I don't think it's a worthwhile endeavor to try and get too specific. If you really wanted to, you could sort of go look up all the different what are called electron configurations of F-block elements, and you could memorize each one separately. You might be able to glean a rule or a pattern for some of the elements in the F-block, but it wouldn't last for very long. So I don't recommend that, tell you the truth. So I don't think trying to predict F-block valences or generally speaking, beyond the s and the d orbital electrons, figuring out whether an f orbital is involved or not, it's not really worth your time. But for s, p, and d, I definitely recommend remembering these valencies. They are consistent and these rules do not change. So for s, p, and d block elements, the rules are consistent and they are worth remembering. They're worth your time to remember. Okay. We're getting closer, I promise you. We're going to draw some orbital energy diagrams today. 3 rules for drawing ground state orbital energy diagrams. Again, as I mentioned, the ground state just means the lowest energy state. We're really not going to focus too much on drawing excited state or high energy state orbital energy diagrams for the most part. So these are by default the only ones we're really going to draw. Lowest energy state. Okay, these are the 3 rules. The Pauli exclusion principle. Pauli exclusion principle. This rule is unbreakable. Unlike the other 2, which really only apply to the ground state, the Pauli exclusion principle applies to every atom everywhere in the universe, and it is unbreakable. Orbitals, no matter the energy level or the size or the type of the orbital or the shape, whatever you want to call it, can never, ever, never, ever hold more than exactly 2 electrons. Now they can have 0 electrons, that's fine. You can have an empty orbital. You can have 1 electron, that's fine too. Or you can have 2 electrons, and that's also fine. But if you do have 2 electrons, make sure those electrons are up and down. Make sure those electrons are pointed in opposite directions, or what's referred to as anti-parallel, meaning they're parallel, but they're pointed in opposite directions. I'll explain later why. Right now, we'll just, for the time being, just remember that part of the Pauli exclusion principle is that electrons must have what's called opposite spin, pointing up, one points up, one points down. The reason, the reason for this, like everything else in quantum mechanics, breaks down to math. The Schrodinger equation says so. So 2 electrons maximum in any orbital, no matter how big the orbital looks like. When you look at a picture of a d orbital, for example, it looks like there's a lot of room. It doesn't matter. 2 electrons maximum, whether you have the tiniest s orbital or the most dispersed d orbital or f orbital with lots of lobes and seemingly lots of room for lots of electrons, it doesn't matter. 2 electrons maximum. 0 electrons minimum. Okay, so that's the Pauli exclusion principle. The Aufbau principle. Aufbau is German for build up. This rule is not 100% followed necessarily, but for the most part it is. You must fill in your lower energy, well, certainly in the ground state you follow this rule because you want all the lowest energy orbitals to be filled before you start putting electrons in the higher energy orbitals. That's all it means. It means you fill up the ground floor before you start filling up the 2nd floor, and then before you fill up the 3rd floor, etc. So fill the lower energy orbitals with electrons before putting any electrons in the higher energy orbitals. I liken rule 2, the Aufbau principle, to this idea of putting marbles in a jar or putting marbles in a vase. So imagine you have a vase and you're dropping marbles into that vase. So you drop a marble into the vase. Well, where does the marble go? Well, the marble drops all the way to the bottom. And in a very real sense, that is following the Aufbau principle because energetically speaking, the bottom of the vase or the bottom of the jar is the gravitationally lowest potential energy, meaning the marbles are achieving or seeking the lowest potential energy, gravitation-wise. Here, what's attracting the marbles in the direction they're going is gravity. In an atom, Instead of gravity, it's the nucleus, the positive charge that's grabbing those electrons and pulling them downward toward the lower energy levels. Now, what if you put a marble in and it stopped right there in the middle of a mostly empty jar? You would probably call an exorcist, right? If you dropped a marble into a jar and it stopped right there, mid-height, hovering in air, I think you'd be pretty freaked out, right? Because it would violate what you have already come to know intuitively and instinctively as a fundamental law of nature, which is that particles seek their lowest energy level, their lowest potential energy level. In this case, these marbles are seeking their lowest gravitational potential energy. They're falling to the point where they can't fall any further. They're at their lowest energy. They have no more energy to expend in movement. Well, substitute gravity with a positive charge, substitute marbles with electrons, and you have exactly the same setup. Gravity is not, electrons are not massive enough to really be affected too much by gravity. They are free floating and they aren't affected, but they are affected by positive charge. In fact, it's the positive charge in the nucleus that's really the biggest force acting on electrons, and it's pulling them downward. Which way is downward? Wherever the nucleus is downward. There is no absolute down or up. There is simply the direction toward the force that's pulling you. For atoms and for electrons in atoms, that force is the positive charge in the nucleus pulling toward the center. For us, it's the gravitational force pulling us toward the center of the Earth. We may think of it as being down, but technically we're being pulled toward the center of the Earth. So just as marbles don't hover in midair, electrons generally do not hover in the middle of a set of orbitals. Instead, they fall all the way down to the lowest type orbital. If there's an s orbital that's open and available, the electron will inhabit the s orbital. If the s orbital is filled, if the 1s orbital already has 2 electrons in it, guess what? That electron is going to have to take the next higher level. And the next higher level, and they stack up just like marbles filling a jar. They will stack up higher and higher, not because they're floating, but because they're sitting on top of each other. That's the way electrons are. But electrons, of course, are not touching. They're sitting on top of each other in a regimented configuration that is dictated by the orbitals. Okay, so that's the Aufbau principle. Fill up your lower energy levels before the higher energy orbitals. Put your marbles at the bottom of the jar before they reach higher up, which is not really a rule we have to enforce. Gravity does the work for us. Hund's rule. Hund's rule, this is a person's name, Hund. Electrons occupy degenerate orbitals. Remember, degenerate means same energy level. Multiple orbitals, all with the same exact energy, one at a time, if possible, with parallel spins, as opposed to anti-parallel. Parallel spins meaning all pointing in the same direction. When they are in separate orbitals, the electrons they point in the same direction. When they're in separate orbitals, when they're in the same orbital, they must point in opposite directions. But when they're in different orbitals, they all point in the same direction, either all up or all down. It doesn't really matter which one you start with, although by convention, you start with all up first. Only when all the degenerate orbitals are half filled. What's a half filled? Half filled, well, if the maximum number of electrons is 2, a half filled orbital is one that is an orbital that has only 1. Half filled, having half of 2 or 1 electron in an orbital, or half the total number of electrons, possible in a subshell. And so the example here is instead of writing something like this, if we have 3 electrons to spread over 3 orbitals, instead of doing this, putting 2 electrons in one orbital and then another electron in another orbital, instead we spread the electrons out. Why do we do this? Electron-electron repulsion. Remember, electrons are negatively charged. What do negative charges do to one another? They repel one another. What do positive charges do to each other? They repel one another. Like charges repel. Only opposite charges attract, but like charges push each other away. So an electron would much rather be in its own orbital rather than experiencing the pushing away power of its fellow electron. Only when you've run out of room, only if you were to try to add, say, for example, a 4th electron to this group of 3. If I had one more electron to add to these 3, only then, once I have no more degenerate orbitals, once I have no more empty orbitals, would I then fill in a single orbital with an anti-parallel pointing in the opposite direction electron. But as long as I have enough empty orbitals, I will put 1 electron in each. The analogy I like to use is that when I get onto a bus full of strangers, I always look for an empty seat because I'd rather sit alone. Electrons are the same way. They would rather go and find an empty orbital to inhabit, but only if they cannot find an empty orbital will they pair up with one other electron in an orbital, a half-filled orbital. If there are no seats, I'd rather not stand, so I will sit next to a stranger on a bus or a train. But if I can sit by myself, I will. Just imagine how strange it would be if you were the only person in a train or a bus and someone came and sat right next to you instead of sitting in an empty seat. That would be abnormal behavior. Likewise with electrons, it would be very abnormal. This situation right here would be incredibly abnormal for an electron because an electron, rather than taking this empty spot over here, chose to sit next to a fellow repulsive electron. Remember, negative and negative repel. Why would it do such a thing? The only reason it would do such a thing is if it were forced to by some sort of outside energy. Now that would be referred to as sort of an excited state, a state where it's not the lowest energy state, it's not the most common state or the state that the electron would normally pick. There must be something driving such a thing. We're not going to surmise what that could be. It's really not relevant to us. The bottom line is when we're talking about ground state electron configurations, we follow these ground state rules, and this simply doesn't happen. Instead, you follow Hund's rule, put them in one at a time in degenerate orbitals until you run out of empty orbitals. Then you can start pairing them up. A pair is 2. Then you can start pairing them up. So rather than having 1 unpaired electron, I would have 3 unpaired electrons. Another way I suppose you could think about this is you want to maximize the number of unpaired electrons for a given subshell. Now, don't start putting electrons by themselves all over, across different energy levels. It doesn't work that way. Within a single subshell, within a single energy level, this is what you do. You maximize the number of unpaired electrons. Unpaired simply means the electrons have no pair. They have no partner inside the orbital with them. Unpaired. This here, if I were to draw an orbital like this represents paired electrons. They're paired up. So I have 0 unpaired and 1 paired of electrons. They're paired up. We're going to use that terminology to a certain extent as well. So keep in mind, paired versus unpaired. It's one of the ways you can tell whether an atom or an ion is magnetic or not, and the type of magnetism it will display as one of its physical properties. So keep that in mind, paired versus unpaired. We'll go into more detail soon. Okay, where are we now? Finally, we can get to some actual examples. I'm sure you've been waiting for this. Here we are. So I'm going to select some main group elements from hydrogen to argon. I have not drawn them ahead of time because I wanted you to watch and follow along with me. So now's a good time to pause the video, grab yourself a sheet of paper and walk through this with me. And then once you're done, or once we're done with these next 3 or 4 slides, I want you to go back, print this out or write it on another sheet of paper, do it all over again by yourself and match your answers to the ones here. It takes practice, but it's actually, with practice, you will get this. So I'm going to start, I did write one element, and that's hydrogen, but this entire space is not devoted to simply hydrogen. So our very first element on the periodic table, element number 1, is hydrogen. So these are examples of ground state orbital energy diagrams for the main group. I'm going to pick a few main group elements that also happen to be, by the way, neutral. And then we'll work on the orbital energy diagrams for cations and anions. We'll see how to handle extra electrons or a deficiency of electrons, meaning extra electrons meaning a negative ion, or a deficiency of electrons, meaning having lost electrons, a cation, a positively charged ion. But for now, let's start with neutral, and let's start with the simplest types of elements, the main group elements, the S block and P block elements from the first 3 rows, maybe the 4th row. Let's start with hydrogen. So the way I'd represent the electrons in a hydrogen atom, actually, there's only one, right? Hydrogen, a neutral hydrogen has only 1 electron, 1 proton, 1 electron. Hydrogen has 1 proton, therefore, if it's neutral, it can only have the exact same number of electrons, which is 1. So how do I represent that 1 electron? Simple. I draw a straight line here. Let me just pick my color. Let's go with dark blue. So I draw a line here. You can either make it a line or a box. I'll leave that up to you. I tend to use lines, but if you wanted to use a box, you could. Some people, I think they like the box because it sort of encompasses, it feels like an orbital. It encompasses or houses the electrons. Perhaps that's the reason. Maybe the graphical representation of a little house for the electron is more appealing. I can certainly see that. Either way you represent the orbital, one thing you have to do, this is a necessity because a person doesn't know what you're talking about. Since all the orbitals look exactly the same, you have to label your orbitals. So I'm going to label this. Well, where is the hydrogen atom? Well, it is in row 1 and it's in the S block. So energy row 1 of the periodic table for an S block element is energy level 1. And we are in the S block, it is an S-type orbital. So 1s is the name of this orbital. It's the energy level and type of orbital. Likewise here, you would have to label this. Even if it's a box, of course, you still have to label it. How many electrons? 1 single electron. 1 electron. So we draw that 1 electron. I'll use a different color here. I'll use light blue. I'm going to draw, by convention, I'm just going to draw the electron as an up first. You can make it a down if you want. It doesn't really matter. 1 electron. And that's it. That's the complete ground state orbital energy diagram for hydrogen. Oh, I'm sorry, here. Or if you want to represent it in a box, you can do it this way as well. An arrow, this is not a 1, this is an arrow. 1 electron, an up electron, a spin up electron. We'll talk about spin later. Inside of a 1s orbital or inhabiting a 1s orbital. That's it. Let's try another element. How about helium? Helium is the very next element on row 1. So helium. Helium, again, we have a single s orbital. Again, we do not write 2s. Remember, the number up front is not the number of orbitals, it is the energy level. Helium has only 1 orbital, and it happens to be an s-type orbital, and helium, again, is an s block element. Therefore, the energy level is first. Energy level, N equals 1. That's why we're writing a 1 here. The 1 has nothing to do with the number of orbitals. It has everything to do with the energy level. It is the energy level. So helium has how many electrons? Well, a neutral helium has 2 protons. It's atomic number 2, right? Z equals 2, atomic number 2, 2 protons. Therefore, in order for it to be neutral, it must have 2 electrons as well. We are only doing this for neutral elements. We'll deal with ions soon, but for now, we're just going to deal with neutral elements. I'm not going to do the box one anymore. It's just not my cup of tea. But if you want to draw boxes, more power to you. That's perfectly fine. I realized because I had to, don't take this to heart as far as the relative energies here. I put energy over here. I didn't draw the helium s orbital higher. If anything, it's actually lower in energy than the hydrogen. I'm only putting it higher because I had to draw my helium in, not because there's anything higher in energy about helium's orbital. In fact, helium has a lower energy s orbital, not a higher energy s orbital compared to hydrogen. And I'll explain that. That'll become clearer later when we talk about relative ionization energies and the drawing power of having more protons in the nucleus compared to fewer protons in the nucleus. Okay, so 1s, and then we have 2 electrons because 2 electrons makes for a neutral helium atom. So I put 1 electron pointing up, and then per the Pauli exclusion principle, I put the other electron pointing down in the same orbital. And that's it. I have a single s-type orbital, energy level 1 for helium, 2 electrons, both of them fit into the same orbital. If I don't need new orbitals or higher energy orbitals, then I don't draw them and I don't create them for no reason. And I certainly don't put electrons in higher energy orbitals as long as there are lower energy orbitals available. The Aufbau principle, the buildup principle says, if there is a spot, if there is an opening, for example, if there's an opening in a low energy orbital, then I must put my electron there. And so that's where I put it. I don't try to shove this electron into some other higher energy orbital if I don't have to. It's a possibility, but that would not be the ground state. That would be what's called an excited state, a higher energy state, where an electron has been dosed with some amount of energy and has jumped up to a higher energy state. And that happens, and that does happen, and we will see what causes that. Okay, so hydrogen, helium. Let's continue on. Let's do the very next one. We're not going to go through every single main group element. Don't worry. So the next one, let's do lithium, element number 3. So lithium, still in the S block, right? Lithium is right below hydrogen. However, something has changed here. Lithium has a total of 3 electrons. Lithium has 3 protons and 3 electrons to be neutral. There are lithium ions, of course, but we're not going to do the ion right now. We're going to do the neutral atom, which has the same number of electrons as the number of protons. So lithium, 3 electrons. Okay, so the lowest energy level available to lithium is the 1s orbital. Now you might be objecting right now saying, wait a minute, lithium is in row 2, not row 1. That's true, but the inside of lithium doesn't know that. The inside, all elements contain all the orbitals, all the lower energy orbitals of the elements that came before them. I'm going to repeat that. All elements contain all the lower energy orbitals of the elements that came before them in the periodic table. So as we move from left to right and from one row to the next row, going down, we're adding electrons to either existing orbitals or building on top of the lower energy orbitals. So even the largest atom, oganesson, element number 118, still has a 1s orbital inside of it, and a 2s orbital, and a 2p orbital, and so on. It has all the same orbitals of all the elements that came before it, plus it has 1 more electron in the last final orbital. So every element builds on or contains orbitals that builds on top of the ones that came before. So the center of lithium looks just like helium. Okay, so when I fill this in, I'm going to put 1 electron like this, another one like this. So this looks just like helium. And in a sense, lithium has a helium core. The interior electrons of lithium, the non-valence electrons of lithium, actually have a configuration just like helium. However, we need a total of 3 electrons. Where do we put that third? Now we have to create, not create, but now we have to represent the fact that there must be another higher energy level. What is that higher energy level? I'm just going to put it a little bit offset here. Well, I guess I have enough room. Sometimes you'll see these things going diagonally. That's not because of anything. There is no horizontal axis. The vertical axis, as you may or may not have noticed, is energy. EV is electron volts. It's a very small amount of energy. The arrow here represents different energies. So we're just drawing this. We're just drawing these orbitals at different energy heights. The higher up you go, the greater the energy of the orbitals. If I go diagonally to the right, it's only to save space. It actually had the horizontal. There is no horizontal axis. There is no meaning to the horizontal portion of this. If I move it sideways, it's only to save space. It's only so I can overlap some of these labels. That's all. Otherwise, I'd draw them right on top of each other like I'm doing right now. But as we add more energy levels, I'm going to have to save some vertical space and move sideways. Okay, so lithium, 1s. What's the next one? Well, lithium is located, its valence electrons are going to be in energy level 2. But lithium, we are still in the s block, so 2s. How many electrons? Well, it only takes one more electron to reach lithium, so I put 1 electron. This is a half-filled 2s orbital. And it's important to get this terminology down. It makes communication, it makes the comprehension of these principles a lot easier if you get all this terminology down. Half-filled 2s orbital. So the core is completely filled, a completely filled 1s orbital, and the valence electrons, so there's 1 valence electron sitting in a 2s orbital, and then we have 2 core electrons in the first energy level, level 1. Level 1, n equals 1. So that's how you describe this. And we have, also another way you can describe it is we have 1 unpaired electron, meaning that a lithium atom will actually be responsive or be affected by a magnet. It will be drawn to one or the other pole of a magnet. It's magnetic. It's what's called paramagnetic. The existence or the presence of an unpaired electron means you have an uncanceled out magnetic field being generated by the electron. We'll talk about that later, but just keep that sort of thing in mind. We are going to talk about that a little later. I'm sort of feeding you previews of future concepts, meaning the part 2 of this video. Okay, so far we've gone through 3 elements. It seems like it's slow going, but we're going to skip around a little bit. The next element I want to do is I'm going to jump from lithium to boron. And the reason I want to do that is because I want to go to our first p block element. So far we've just been dealing with the s block. It's time we moved out of the s block and into the p block. And but just to show you what's going on the periodic table, what have we been doing so far? Okay, let's clear some of this out. Let me just make a little bit of room here. Just a little. Okay, so far what we've been doing is we've been filling in electrons one at a time. So we had 1s electron, and we put 1 here. We had 2 1s electrons for helium, which we put here, like that. So we're adding electrons, 1 electron, 2 electron. Then we come over here, 3 electrons for lithium. This is where lithium is, lithium. And we have 1s, we had 1s2, and then we have 2s1. And then for beryllium, it would be 2s with 2 electrons. Now we're going to jump, we're going to skip beryllium, Be for beryllium. We're going to skip beryllium. We're going to move on over to boron, B for boron, which is a p block element. but still on row 2. So we're changing orbitals now, but we are not changing energy levels going from lithium to boron. Let's go back now. But if you notice, all we're doing is following the periodic table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you go start over again, left to right, you move across, go to the next row, start again, go all the way across. You simply move across the periodic table, adding electrons and adding orbitals as you need them. When you fill up an energy level, when you fill up either an energy level or an orbital or a subshell, you simply create the next energy level, and you can actually use the periodic table to guide you. As you fill up your 2s, it tells you, the periodic table tells you, okay, now it's time for 2p. Now it's time for the 2p's, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Now, once you've run out of space there, it's time to go to 3, 3s1, 3s2. And then once you've run out of room in the s, you jump to the p block, but on the same row, 3p, 3p1, 3p2, 3p3. You keep adding electrons to the p subshell, to the 3 orbitals of the p subshell, and so on until you run out of room. And then you let the periodic table guide you. We are literally following, we are reading along the periodic table. And if we're dealing with neutral atoms, the atomic number matches the total number of electrons. If we're dealing with ions, then you have to account for the fact that if you're dealing with a positive ion, you have that many fewer electrons. If you're dealing with a negative ion, you have that many more electrons than neutrality. Okay, let's go back now. So now we're going to do boron. And since this is a p block element, I'll tell you what, I'll color code it just to distinguish it from the others. So boron has a total of 5 electrons. We are at atomic number 5. We are now in the p block, but the fact that we're in the p block doesn't change anything about the interior or the previous electrons. We still represent all the former orbitals and their electrons. We're simply building up. We're simply adding another electron to what was already there. Or if needed, we add another orbital if we've run out of space in the lower energy levels, which we have. So let's do this. Let's go with green. So here we have, sorry about that. Here we go. Okay, so start again. 1, we have 1s. 2, we have 2 electrons in the 1s. That's the very core of boron. Again, the core of boron looks just like helium. Boron has a helium core because the level 1 energy level is the core. The valence electrons are the highest energy. Since this is a p block element, the valence electrons are both the s and the p orbital electrons, but those of the highest energy level. So then we have 2s. By the way, this time I am being intentional. I'm drawing the orbitals a little bit lower than lithium because as you move from left to right across the periodic table, the elements do have lower and lower energy level orbitals. They're the same energy levels, but those particular energy levels within a different atom have different energies. Anyway, 1s, we have 2 electrons, 2s, well, this would be 2s lithium, 2s beryllium, L lithium, beryllium. So the 2 electrons representing lithium and beryllium are there in the 2s orbital. But we need 5, right? We need 5 electrons. So far, we've only got 4. Where do we put the 5th one? Do we put it here? No, of course not. We can't do that. Pauli exclusion principle says we can't put any more electrons into an orbital. So what do? Well, the periodic table tells us now it's time to jump to the p block. We jump in the same row, we jump across to the other side of the row to where the p block is. B, boron, is a p block element, but it is still in the p block. Excuse me, it's still in row 2, but it's in the p block. Okay, now we are still in the same energy level. Nevertheless, I'm going to draw the 2p orbitals, the subshell, higher in energy. Why? Remember what I said, even though the energy level might be the same between the 2s and the 2p, p orbitals are always higher in energy than s orbitals. Remember the order. S is less than p, which is less than d, which is less than f. S is the lowest energy. Given the same n value, for all the same n values, S is lowest, F is highest. So S is less than P. Okay, let me write it the other way, so I'm consistent. S is less than P in energy. Because it's less than P, S is down here, 2S is down here, 2P is up here. How many orbitals do I draw? Regardless of how many electrons, even if I only need one orbital to house one electron, I must always draw all three of a subshell. Never leave off the other orbitals, even if you have to leave them blank. They are a set. P orbitals are a set. Don't break them up. Don't break them up. I'm not going to write that. Always keep all three together. Don't write just one p orbital. That's never correct. Always write all three orbitals. If there's a subshell, write all the relevant orbitals for that subshell. If it's a d subshell, draw lines to represent all 5 of the d orbitals. You don't have to label them, by the way. I do not have to label them px, py, pz, etc. You don't have to do that. 2p already stands for x, px, py, pz. Now, if you want to do that, you're welcome to it, but you don't have to. Most people understand what it means just to write 2p. Now, you do have to write the energy level, and of course, you do have to write the type of orbital, but you don't have to specify which one of these is px, py, pz. It really makes no difference because they are degenerate. Remember, they are all on the same energy level. And so they are all located, whatever this number, this energy level would be. Let's say, for example, it's, I don't know, 13 electron volts or whatever. They are all 13 electron volts. These are degenerate. This is a degenerate set of orbitals, the p subshell. Okay, so we have 1, 2, 3, 4. We just need one more electron. I guess I'll stick with green. So we just need one more. It doesn't matter where you put it. I'm just going to put I prefer to go from left to right. So I'm just going to put my one electron, and I prefer to put up arrows rather than down arrows at first. If you like down arrows, draw a down arrow. That's perfectly fine. There's no convention about which one to start with. But if you start with down arrows, make sure they're all down. That's it. That is our orbital energy diagram for the ground state electron configuration of boron, neutral boron. We have 5. So which ones are our valence electrons? Our valence electrons, remember, are the s and the p orbitals taken together. So our valence electrons, we have 3, what is this? We have 3 valence electrons, and we have 2 core electrons. Sometimes you'll have more valence electrons than core. Sometimes you'll have more core electrons than valence. There's no fixed rule about that. You simply count them up. So energy level 2 contains the s and p orbitals contain all the valence electrons. Energy level 1 contains the core electrons for boron. That's for boron because it happens to have only 2 energy levels within its structure. And we have 1 unpaired electron. Okay, let's continue on. Let's do some more. Let's just do we still have some more principles to look at. Notice nothing we've done so far, for the most part, has been redundant. Every new element we look at introduces a new concept or a new rule to apply. And that's going to continue on. So let's do the next one. Let's do nitrogen. I'm going to have to erase some of this. When I save this file, it's most likely going to be blank. I'm going to erase all of this stuff so that you have the chance to print it up blank and fill these in, take notes, fill it in, practice with it on your own. Practice makes pretty good. Do your best with this stuff. Okay, so now let's skip on over to nitrogen. We'll skip carbon for the time being. And we'll move on over to nitrogen. So we have nitrogen, and again, same old thing. We have 1s. By now, this should be pretty repetitive to you. 1s with 2 electrons, 2s with 2 electrons. Nitrogen has a total of 7 electrons. If you look at the atomic number at 7, since we're talking about neutral nitrogen, the number of protons is the same as the number of electrons. That's not because the atomic number represents electrons. It doesn't. It represents protons, but electrons equal protons whenever the atom is neutral. Let me just draw a line in between these in case it looks like they're going to get mixed up. Let me just separate these out like this. Okay. Okay, so 1s, 2, 2s, 2 electrons, 2p. So now we have our 2p subshell. And again, as always, we draw all 3 of the orbitals. Are we going to need more? No, I can tell you right now we're not. I mean, there may be situations where you will need more orbitals, higher energy orbitals, but usually you can tell. You can tell that's not true because nitrogen is a 2p block, is a p block element, and it's only on the second row. So you know you're not going to need anything beyond the second row. And 2p is the end of row 2, right? The row of the periodic table always ends with the p block. If you notice, the end of the p block is the very end of the periodic table. We're moving from left to right across the different columns, left to right across the periodic table. So these are eminently predictable. We're simply moving from left to right across the p block, adding electrons to orbitals as we go across. Now, this time, we've been using the Aufbau principle since lithium. We applied the Pauli exclusion principle to helium. We use the Aufbau principle with lithium. Now we're going to apply Hund's rule for the first time, which tells us that rather than, so we have 1, 2, 3, 4, we need 3 more electrons. Rather than writing our electrons like this, Hund says no. Right? We can't do that. Hund's rule says, no, we should not be doing that. We should not be pairing up electrons. In fact, in a degenerate subshell, a degenerate set of orbitals, we should maximize the number of unpaired parallel electrons. So instead of cramming them all together into orbitals like that, we're going to spread them out. Just remember, Hund's rule says spread out, at least as much as you can. Spread out. So let's spread them out. So rather than cramming all 3 of our electrons into those 2 orbitals, we're going to apply Hund's rule, and we're going to draw them parallel. 1 electron. We need 3 electrons, right? So 1 electron, 2 electron. Notice they're all pointing in the same direction. 3 electrons. Hund's rule says spread them out. And make them parallel. When I say parallel, I mean pointing in the same direction. Of course, they're lines and they're parallel to each other. They're not pointing sideways. But what I mean by that is pointing in the same direction. So we have, do this little double check. Make sure you have the right number of electrons. 1, 2, 3, 4, 5, 6, 7. Yeah, we have 7 electrons. Neutral nitrogen, atomic number 7, does have 7 electrons as well. We have the total. Always do that little double check. It's easy to make a mistake for anybody. I've made mistakes. Anybody can make a mistake. So double check your work, always. So we have 7 electrons. Oh, and another thing is just do these little double checks where you just confirm for yourself the core, the valence, etc. I'm going to stop counting the core electrons for now, but I'll leave that to you. But we do have 1, 2, 3, 4, 5. We have 5 valence electrons. 5 valence electrons. And we have 3 unpaired electrons. 3 unpaired electrons. Five valence electrons altogether, and 3 unpaired electrons of those 5 valence electrons. Notice your core electrons are always paired up. Oh, I'm sorry about that. Let me go back. Notice that your core electrons are by definition going to be paired up in the ground state. They have to be, because a complete shell or a complete orbital always has an even number of electrons, and that means they are always completely filled. You cannot move on to a higher energy level before you fill in the lower energy levels. Now, we are going to see that Aufbau principle is going to be kind of violated later on. Don't worry too much about it. It's not an ironclad rule. Unlike the Pauli exclusion principle, some of these other rules do get violated occasionally. That's because the energetics of the situation change. And especially as you go higher and higher in energy levels, the energy levels are not separated by too much energy. If that sounds like, that sounds a little abstract and complicated right now, it'll become a little bit clearer as we move on. I just want to remind you through all of this that the importance of energies of electrons and their orbitals cannot be overstated in chemistry. There are whole fields devoted to programming computers with the algorithms to calculate energies ever more finely within molecules and compounds, calculating the energies of these orbitals and the energies of the electrons to figure out where the electrons are going, where the electrons are going to be happiest, where they're going to find their lowest energy state, so you can predict, rather than doing a bunch of experiments in chemistry in the lab and wasting a lot of materials, spending years on dead ends. You can actually run computer simulations to calculate the energies, and those will sift out some of the more probable and less probable pathways to making a compound, a chemical, where the electrons are more likely to flow in a way to cause the atoms to recombine to make the chemical you want, as opposed to the pathways or the methods where you'll get nothing from trying to combine your atoms to make new chemicals. The point is this: all chemistry boils down to the movement of electrons seeking lower energy states. That is all of chemistry. If we knew everything about the energies of electrons everywhere, you could pretty much consider the field of chemistry closed. The case closed, it would be done. We'd all be finished and we'd all know everything. And we'd be able to make anything we could imagine. But that's not the way it works. There are very fine, subtle distinctions in energies once you start combining atoms together. Now, let's continue on. Rather than going to the next element, which will also elucidate kind of another point I want to make, although a fairly minor one, I'm going to jump down a level. Only because, I think by now it's getting fairly predictable what I'm doing, right? And that's fine, and it should be. This really is as predictable as it seems. In fact, you can almost sing a song with this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. At least up through the calcium, it's always the same pattern: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. 1s, 2s2, s, and then sp, and then sp again, and then s, and then finally when you get to row 4, you've got an intervening d block in between your s and p block. That's the only thing that destroys that pattern or ruins that pattern. But even that's not too complex. S, sp, sp, sdp, 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 sfdp, sfdp. That's it. SP, SD. Ultimately, you're doing SDFP or SFDP. You're just going in the same order that the periodic table from left to right presents the blocks or presents the elements to you. All right, let's jump down to sulfur. So the next example I want to do is sulfur. And here I'm going to have to make a little bit of room. So I'm going to use this space right here. The reason, instead of jumping to oxygen, I'm going to jump to sulfur. And that's simply because I just want to get out of row 2 and get into row 3. That's all. That, and I also want us to just take a look at a situation where we do have another electron to add to a half-filled p subshell. Oh, that's one more thing. That's another way to describe this is, let me use red. Here, that's one more way to describe this is we have a half-filled, an exactly half-filled p subshell. Half-filled p subshells are actually fairly stable when it comes to the d subshells. Not so much for p, but for d, they're actually fairly stable. There's something special about either a half-filled subshell or a completely filled subshell. Nature seems to prefer that sort of symmetry, that sort of even filling of the orbitals in a set of orbitals. Okay, let's do sulfur now. Sulfur is element number 16, element number 16. Yes, I had to look it up. Okay. Let's go with purple. So we have sulfur. S is the chemical symbol for sulfur. Again, don't mind too much about the relative energies here. Don't pay too much mind to these as far as comparing one atom to another. So again, no matter how big the atom is, we are going to start from the beginning. 1s. The very center of the S of sulfur is the 1s orbital, the very inner core electron, 1s. Then we have 2s, 1s2, 2s2, 2p6, right? Because we know we're going to fill up all of the s orbitals, all of the p orbitals through row 2, and even through row 3 orbital s. So even through the 3s, we know we're going to fill that up because the sulfur is in the p block of the third row, or the third energy level p block, which means we know we're going to fill up all these orbitals I've just listed here. The only orbital or the only subshell that we're not going to fill is the 3p subshell. 1, 2, 3 orbitals. And so now we start, so these are 1s2, 2s2, 2p6, 3s2, 3p4. In fact, if I wanted to write this in a sort of shorthand notation, which we're also going to learn, it's called the electron configuration. The electron configuration of sulfur is 1s, and we represent the total number of electrons in either orbitals or subshells. We just put the total number, and we represent them with superscripts. These are not squared, these are superscripts. 1s2, 2s2, 2p. Well, the p orbital, p subshell is completely filled. We know that because sulfur is well beyond the second row, which means we filled up all the orbitals, 2, 4, 6 electrons filling the p, so we have 6 electrons. Notice again, I'm not going to try to individualize the orbitals. I'm not going to write px, py, pz. It's understood that 2p refers to 3 different orbitals. Just, it's understood, so you don't have to write it, but I'm going to write it here just for you, just because we're learning this now. 2px, 2py, 2pz, each one of these has 2 electrons for a total of 6 electrons. We don't write E, we just write a superscript 6 to represent those 6 electrons. 2p6, 3s2, 2 electrons in a 3s orbital, energy level 3, s-type orbital. And then finally, we have 3p. Now, sulfur has 4 electrons. just count from the very beginning of the P block, and you'll see that it's 4. In fact, here, if you have any trouble at all, let's go back to the periodic table over here. Okay. Let's, wish I had a larger eraser. So sulfur is on the third row. Now don't let it fool you over here. Row 1 is up here. There just don't happen to be any elements in row 1. Row 2, row 3. So we have aluminum, Al. We have silicon. We have we have phosphorus, and we have sulfur. Here we are. So we have in the P block, we have 1, 2, 3, 4. It is the 4th P block element. So therefore it has 1, 2, 3, and then it has a 4th electron somewhere in there. And we're going to see how to do that. So if you ever want to know how many electrons to put in a particular subshell or block, just count from the very beginning of that block and just count the boxes till you get to that element. Or if you want to know how many electrons are in the valence shell, the valence electrons of an element, just go back to the very beginning of the row that that element is on and just count the number of boxes. If it's a P block element, count the number of boxes, but exclude the D block. If it's a D block element, count the number of boxes from the very far left of the periodic table all the way to whichever D box you happen to be in. Okay, let's go back now and continue on here. So we have sulfur. So this would be what's called the electron configuration. It's not as informative in terms of, and certainly you can see it doesn't really represent the energies, the relative energies of the orbitals. It also doesn't tell you whether elements are paired or not paired. So for example, 3p4 might give you the wrong impression. Seeing that there's an even number there, you might think that those are just 2 pairs of electrons and all the electrons are paired in this, but they're not. They're actually 2 unpaired electrons. So let's go through sulfur. 1s2, 2 electrons. We know that has to be the case because sulfur is all the way on the 3rd row, P block. Everything before that must be filled up. So all these orbitals are filled. 1s2, 2s2 electrons, 2p, 1, 2, 3, 4, 5, 6. So even though I fill them in according to Hund's rule, at the end of the day, the 2p subshell is completely filled. All the electrons are paired up for a total of 6 electrons in the 2p subshell. Then we continue on. Then we go to the next row, row 3, and we start again. 3s1 takes us through sodium. 3s2 gets us to magnesium, Na, and then Mg. Then we jump over to 3p, 3b, aluminum. What did I just say? Silicon. Phosphorus, and then finally, where do I put the last one? Now I've run out of space. I have this half-filled subshell, but I have 1 more electron to add. I simply add my next electron to one of these, and of course I put it with opposite spin. Opposite spin. So Pauli says opposite spin when they are in the same orbital, but same spins when they are in different orbitals. And that's it. So we have 1s2, 2s2, 2s2, 2p6, 3s2 electrons, and then finally 1, 2, 3, 4, 3p, 4 electrons. And then you put all of these together and you get what's called the electron configuration of sulfur. The electron configuration. That's all an electron configuration is. It's just a watered down, simplified version of orbital energy diagrams. Personally, I don't really like them that much because because they don't give me the information I need. Note that we have two unpaired electrons. Now, if you were very naive about the elements, you might look at this 4 and conclude that they are paired, or at the very least, you don't know, paired. But if you look at this, you can clearly see two unpaired electrons. What about the valence electrons? Well, the valence electrons are going to be your top energy levels, the 3. Energy level 3 is the valence energy level for sulfur. So that's going to be these right here. That's a total of 1, 2, 3, 4, 5, 6. So we have 6 valence electrons. By the way, oxygen, which is the element just above sulfur, also has 6 valence electrons. Selenium, the element below sulfur, also has 6 valence electrons. So does tellurium. In fact, every element in a given column of the periodic table has the same number of valence electrons as its congeners. A congener, by the way, are just group members. They are the elements in the same column as each other, congeners. I don't use that term very often, so don't worry too much about it. And I don't hear it that often, but congeners, elements in the same family or group or column. All of these mean the same thing. Family, group, and column are just, they all refer to the vertical arrangement of the elements in a given column. So congeners, con, together or with, generated. They're generated from the same place or the same way, or they generate the same things. So 6 valence electrons, 2 unpaired electrons, and of course the rest of these are going to be your core electrons. We won't bother counting them, but you can count them if you wish. These are all your core electrons. Notice as you get further down the periodic table, you're going to have a lot more core electrons and a lot fewer of the valence electrons, relatively speaking. That's because it's really the only outer shell of the atom that are your valence electrons. Sort of like the outer peel of an onion. Most of the onion is interior, it's only the outer shell that peels away. Likewise, it's only the electrons in the outer shells that peel away, that can be peeled away from an atom. Okay, so those are, more or less, those are all the possible examples. I mean, everything else is just going to repeat some of the same principles. My advice to you is to go through these examples again and give calcium and potassium a try as well. Make sure you can do all the main group elements, and knowing what you know about the relative energies or the number, energy level number for the d orbitals, give that a try as well. That's going to be in part 2 of this video, is we're going to talk about the d orbital or the d block elements and how we represent their orbital energy diagrams, as well as go into more detail about electron spin, about diamagnetism versus paramagnetism, and a few other concepts. We are not done though. We are not yet done. Let's continue on. I'm not going to do too many of these examples because 1 or 2 should suffice. I'll do a simple example, the hydrogen ion, and then I will do a more complex example where you might find that you have a choice to make as to which electrons to remove. So if you recall, cations are positive ions, positively charged ions. That means you have fewer electrons, fewer electrons than neutral. You've lost, or the atom has lost electrons. It has fewer electrons than before. So taking a look at hydrogen, well, the hydrogen ion, the +1 charge in a hydrogen ion can only indicate one thing. Hydrogen had only 1 electron to begin with. So what's the electron configuration or the orbital energy diagram for hydrogen with a +1 charge? A +1 charge, remember, indicates the loss of 1 electron. Well, it only had 1 electron. So the protons minus the electrons equals the charge, right? Okay, so the protons, 1 proton minus electrons equals +1. Therefore, the electrons equal 0. No electrons. So we have no electrons. So the way to write this is simply to write 1s, and that's it. No electrons. And it's likewise, its electron configuration would be 1s, 0. No electrons. That's not a degree sign, that's a 0. Easy peasy, actually. I simply don't include any electrons because there are no electrons. A hydrogen ion has no electrons. A hydrogen ion is a free-floating proton. 99% of the hydrogen on Earth, remember, contains no neutrons. So 99% of the hydrogen on Earth, if it becomes hydrogen ion, positively charged cation, is simply a free-floating proton. Let's try another one. Let's try calcium 2+. No, that's too far up. Let's go for something a little smaller. How about magnesium? So magnesium typically takes on a 2 positive charge. So we have, let's first start with neutral magnesium, and then let's see what we need to do to the neutral magnesium in order to convert it into magnesium dication. Dication just means 2 positive charges. 1s, 2, 2s, 2p. Remember, we draw 3 orbitals. 3s, and that's it, 3s. So we have 1s2. Magnesium is on the 3rd row, and it's in the s block. So we count the electrons. 1s1 is hydrogen, 1s2 is helium, 2s1 is lithium, beryllium. Then we go boron, carbon, nitrogen, oxygen, fluorine, neon, a completely filled 2p subshell. And then we go to the next row, row 3, and we can see that we have sodium, and then we get to magnesium. And there we have it. That's neutral magnesium. So what do we do in order to turn magnesium into magnesium 2+? Actually, we don't really need to draw this over again. What we do is we simply remove the highest energy to make the ion, to make a cation, a positively charged ion, remove the highest energy orbital electrons. The highest energy electrons. Well, which ones are those? Well, actually, those would be the valence electrons in this case. And since we're removing 2, we're removing all of the valence electrons. And that's frequently what happens with metals, is that they lose, at least with main group metals, meaning S block and P block metals, they lose all of their valence electrons. So 3s, we remove both of those electrons to make a positive 2 charge. Remember, a positive charge indicates the loss of that many electrons. A positive 2 charge means we have lost 2 electrons compared to neutrality. 2 electrons are gone. It doesn't mean that we have only 2 protons, and it doesn't mean anything else. I don't know whether there are many ways to interpret that, I suppose, but remember, it's the difference between the number of protons and the number of electrons. Or another way to put it is it's the difference between neutrality and the number of electrons you would have to gain or lose to achieve that charge from neutrality. So the orbital energy diagram for magnesium 2+ would then be this. The loss of both valence electrons. So now magnesium 2+ has 0 valence electrons. Magnesium had 2 valence electrons, but magnesium ion has 0 valence electrons. Only core electrons exist. and no unpaired electrons. All electrons are paired. The 2p subshell is completely filled, as are all the other orbitals. And there you have it. So anytime you need to take away electrons, take away the highest energy electrons first. That's a golden rule. Now, there will be times when it's going to seem a little bit confusing, but for the most part, this is a reliable rule. And if it ever isn't, I will warn you. I will give you fair warning if that's ever not the case. For example, with F block elements, that would be not the case. Those are confusing, and you don't have to memorize them, in my opinion. I don't find it all that helpful for you, so don't worry about F block elements specifically. So always remove, if you need to remove electrons, always remove the highest energy ones first. Remember, we're talking about cations, positive ions. Positive ions, by their definition, involve the loss of electrons. This magnesium has been ionized. And even though the word ionized is generic, it specifically refers to having been turned into a positive ion. Generally speaking, when you talk about ionization, it generally means losing an electron rather than creating a negative ion by adding an electron. Okay, next, let's do an example of a negative ion. And I'm actually going to start, surprisingly, with hydrogen again. Hydrogen, this is not as common as the hydrogen positive ion, but there is such a thing called the hydride ion, a negatively charged hydrogen. Such a thing does exist. In fact, batteries used to be, a lot of batteries used to be nickel hydride. In fact, I think they still do exist. Nickel hydride were rechargeable batteries. Nickel hydride, where hydride was the negative ion hydride. So this time, instead of taking away the only electron in hydrogen, we're actually going to give the electron a little friend, a little buddy. So here we have our 1s orbital. We have our original hydrogen ion. This would be neutral hydrogen. What we do then is we add, how many? We add one electron to get the negative charge. So we add another electron. Again, we pointed downwards because I've made the first one upwards. Opposite anti-parallel spins. If one points up, the other one must point down. There are only two options for electrons. They're either up or down. That's why you can't add three. The real rule for Pauli exclusion is that you cannot have two electrons of the same spin in the same orbital. But since there are only two spins available, up or down, once you've exhausted those options, you cannot put in another electron. There is no sideways spin electron. Once I put an up in and a down in, I can't put another up, that conflicts. I can't put another down, that conflicts as well. That's the real limitation. It's not because of size or anything else. It's because the Pauli exclusion principle only allows for two uniquely defined electrons, meaning their spins, if they're in the same orbital and in the same energy level, in the same atom, everything about the electrons are the same. There has to be something different about them. Otherwise, in a sense, nature won't be able to distinguish between them. And the only thing that's left for them to be different is their spin. Okay, so add one electron, so we add that. So the hydride ion has two valence electrons now. We've actually gained in number of electrons. It also went from one unpaired electron to 0 unpaired electrons. That one unpaired electron has now been paired up. So whereas the hydrogen atom is paramagnetic, meaning it has a net magnetic field of its own, the hydride ion is what's called diamagnetic. It doesn't have any magnetic field of its own. If you're worried, don't worry. I will go over this soon in a future video, but I will go over that. I'm just introducing the topic, that's all. Don't be frightened. All right, now, let's do another one. A oftentimes nonmetals tend to gain electrons in order to achieve an electron configuration or an orbital energy diagram that makes them very similar to their nearest noble gas element. So let's pick something simple. Let's pick fluorine, or actually fluoride. Fluoride is F minus. This is the fluoride ion. By the way, do you notice that IDE is always the ending of an element that has a negative charge? This is always going to be the case. In fact, virtually everything in chemistry ends with either the letters IDE, IT as in Tom, E, ITE, or ATE. So fluoride is an F, a fluorine atom with one negative charge. Okay, so we have one S, we have two S, so one S2, two S2. Fluorine is at near the very end of the second row. So we know that 1s and 2s are already filled because we're past the S block completely on row 2. But now we have to figure out what's going on with the 2p subshell. 1, 2, 3. So let's fill in our orbitals first. 1s2, 2s2, that takes us through beryllium. Then we have boron, carbon, nitrogen, oxygen, and then finally, well, we're at fluorine, but if we stop right here, we've got neutral fluorine. We need to make this fluoride with a negative charge. We need to account for this -1. We need to add 1 electron. Where do we add that 1 electron? Well, I see an empty space right here. And that's exactly where we're going to put that electron. Again, we're going to fill it in. Because the first electron, I drew the first electron up, I'm going to draw in my second electron down. And that is the electron that turns fluorine into fluoride. Notice again, we went from unpaired, having 1 unpaired electron, to having 0 unpaired electrons. Likewise, we've increased the number of valence electrons. We now have 2s and 2p. We now have 2 plus 6. We have 2 of these, 6 of these. We have 2 plus 6 equals 8 valence electrons. We have 8 valence electrons, 0 unpaired electrons now. So fluoride has 1 extra valence electron. In fact, it has a complete set of valence electrons. Another thing we can say is this, and this is a critical point. Another thing we can say is that fluoride is isoelectronic with the noble gas element. Can you see which one I'm going for? Remember, the noble gases are the very last column of the periodic table, the rightmost column, the furthest right column of the periodic table. Fluoride, not fluorine, but fluoride with that extra electron now looks, its electron configuration or its orbital energy diagram is exactly the same as the noble gas element neon. Neon. If we were to draw the orbital energy diagram for neon, it would be indistinguishable from fluoride. Neon equals fluoride. They are isoelectronic. They have the iso, same electronic structure. Neon equals fluoride. Are there any other ions that we could come up with that are isoelectronic with neon? Fluoride is one. Yeah, in fact, there is. There is another one. What about the element right before fluoride? The element right before fluoride is oxygen. So we have 1s2, 2s2, 2p, 1, 2, 3, 4. That's the electron configuration for oxygen. Now, clearly, oxygen, neutral oxygen does not equal neon. It's not isoelectronic with neon. However, the most common state you'll find oxygen in, especially in the Earth's crust, oxygen is the most abundant element in the Earth's crust, but it's not oxygen as in oxygen atoms or neutral atoms. Instead, it's oxygen ions with 2 extra electrons. In fact, it's oxide that is very common in the Earth's crust, oxide with a -2 charge. What does that mean? That means I add, a -2 here means add 2 more electrons to the neutral oxygen, to the neutral form of oxygen. So if I add 2 more electrons, what do I get? Well, I get the same thing. I get a complete p subshell. This also is equal to neon. In fact, we can say that fluoride, oxide, and neon are all a set of isoelectronic, I'll say species. In chemistry, sometimes you use the word species, i.e., that is to say atoms and ions, whatever. But that's not all. You can actually do more. What about a positive ion? Can we find a positive ion that also is isoelectronic with neon? Definitely. In fact, the easiest way to do this is to go to the periodic table. If you want to find all the most reasonable or closely associated ions you can make, you can turn into, that you can make isoelectronic with neon or with any particular element, especially noble gases. One thing you can do, sorry, give me a moment. Let me see if I can actually, no, I can't. Okay. I guess I just have to go through it. It's just a little tiring having to erase all of this. One thing you can do, if you want to find isoelectronic sets of elements or neutral atoms and ions, remember, no 2 neutral atoms can be isoelectronic with each other. Only ions can be isoelectronic with a single atom. To say that 2 neutral atoms are isoelectronic with each other is to imply that they are the exact same element. 2 different elements can't be neutral and isoelectronic because that would imply that they have the exact same number of protons, in which case that would make them the same element. Okay, so neon is right over here. We have fluorine, we have oxygen. Let's go the other way though. If I wanted to find a positive ion that was also isoelectronic with neon, what I would do is I'd look for an element that, when neutral, has more electrons than neon. What does that mean? That means I go further ahead in the periodic table. I go to the next row. I go to row 3 and I look at, oh, well, look at that. I have sodium and I have magnesium. Well, sodium and magnesium have more electrons than neon, but sodium is 1 box away from neon. If I simply remove 1 electron from sodium, sodium will have exactly the same number of electrons as neon. You can even count them. Sodium is atomic number 11. A neutral sodium has 11 electrons. If I take 1 away, I have 10 electrons, which is equal to the number of neons, 10 electrons. Likewise, magnesium 2 plus has 12 minus 2 equals 10 electrons, which equals the number of electrons in neon. So you can simply count the electrons. You don't even need to look at the orbital energy diagram. So sodium positive 1 and magnesium positive 2 are both isoelectronic with neon. In fact, you can go further. You can identify this element right here, aluminum. How many, or what charge, or how many electrons would aluminum have to either gain or lose to become isoelectronic with neon? I'll let you think about that one. That's a little question for you. how many electrons would aluminum need to gain or lose to become isoelectronic with neon? There's a question. And you can get back to me. You can let me know. You can either message me and say, "Oh, I know the answer," or message me and say, "That was a tough one. How do you work that out?" And I'll answer either way. So my recommendation is write out the orbital energy diagrams and or electron configurations of sodium +1 and magnesium +2. Actually, you don't have to write us magnesium +2. We already did it. Look at that. Loss of both valence electrons means this is empty. So you can, for all intents and purposes, you can just delete that 3s. So what's left? Magnesium 2+ looks just like neon. How many electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. 10 electrons. See that? We already did magnesium 2+. Sodium 1+ would simply have one extra, well, it would have the same number of electrons. It would have one, you'd start with one fewer electrons for sodium, and then you'd remove that one extra electron, so still leading to an empty. For sodium 1+, you'd still have an empty 3s orbital. Okay, now we did this for most, so I'm just going to let you go back through this video. I'm going to leave this as an exercise for you, but go back to the previous examples, count the number of unpaired electrons. Now we did that for some at the beginning. You can, if you want, you can count the others as well. Identify and count the number of valence and core electrons. I think we did that all the way through. Identify isoelectronic sets of atoms and ions. So we've already identified a few, if you can spot some more, and I don't know for sure, I haven't actually checked all of them out, but one good place to look is look at I've erased some of them, but look at the neutral, look at some of these neutral elements and see what you would have to do to other elements around them in order to force them to have the same number of electrons. They may not be realistic charges on those atoms, but it might still help. So for neon, we found that there's quite a few ions, both positive and negative, that are isoelectronic. Write the electron configuration of each atom or ion. So let's go back and just do a few of these as examples, since I did give electron configurations a little bit of a short treatment here. Let's write them out for both fluorine and oxygen. Oh, and hydride. And then let's do it for the, see what we have to do for the negative ions of these two elements. So for example, for hydrogen, the electron configuration would simply be 1s, but instead of drawing the arrows, we simply write 1s2. And that's the electron configuration of hydrogen. The electron configuration. Again, the electron configuration is nothing more than a watered down version of the orbital energy diagram. Now, just because I say that doesn't mean I don't want you to understand that. I do want you to be able to understand and even write electron configurations. There will be times when it's going to be helpful for you to do that, but orbital energy diagrams are really where it's at in terms of visually seeing the relationship of energy and unpaired electrons in an atom. And later on, you're going to use these orbital energy diagrams. You're going to put them together to make molecules out of individual atoms by combining one atom's orbital diagram with another atom's orbital diagram to create what's called a molecular orbital diagram. But you'll start from the individual atoms, putting them side by side and seeing what combined orbitals they create when their atomic orbitals overlap each other. That's in a future chemistry course, not this one. Okay, so let's do the electron configuration of fluorine, and then let's do the electron configuration for fluoride. So first fluorine without the extra electron. So just like it's written here, we have 1s2, 2s2, 2p, 2, 4, 5. So 1s2, 2s2, 2p, 5. Notice, by the way, that these superscripts represent the electrons. If I add them all up, 2 plus 2 plus 5, I get the total number of electrons. It should match the total number of electrons that you want to see in whatever your final atom or ion is. In this case, I'm doing fluorine. Now, if I do fluoride, then it's 1s2. Everything at the beginning stays exactly the same. 1s2, 2s2, 2p. Now I have, since I have fluoride, it's not 5 anymore, it's 5 plus 1. I'm not going to write 5 plus 1, that's silly, right? So I'm just going to write 6, 2p, 6. Tell you what, why don't I write it in a different color, just so it'll just pop. 2p6. And what about my total? 2 plus 2 plus 6 equals 10 electrons, which is exactly what we want. By the way, another way to write this, another way to write the electron configuration of fluoride is to simply write it as the noble gas neon in square brackets. So the electron configuration of any element can always be written as a shorthand by using the nearest noble gas written in square brackets. Now, that doesn't mean you can represent any ion or atom. Only the portion that is equivalent to the noble gas can be used. Only the portion of the electron configuration that corresponds to the noble gas's electron configuration can be used. How about oxygen? So we come over here to oxygen. Again, oxide is isoelectronic with neon, so we could represent oxide, O2 minus. We could represent its electron configuration as simply helium in brackets. But let's go through the entire process. So we have oxygen. Again, we have 1s2. We have 2s2. We have 2p. Now, before we added the 2 electrons, let's just do neutral oxygen. We had 2p, 1, 2, 3, 4. 2p, 4. So oxygen, neutral oxygen is 1s2, 2s2, 2p, 4. And oxide would be 1s2, 2s2, 2p. Then we just add 2 electrons, 5, 6, 6. And that's equivalent to square brackets neon. They actually represent the same thing in this case. What about something like, let's go back one. How about magnesium? Let's try neutral magnesium first. Let's do the electron configuration of neutral magnesium, and then we'll do the electron configuration for the magnesium ion. And I'll do it in a few different ways. I'll show you how to use the noble gases as a convenient shorthand, even when the ion or the element, and in this case, the neutral atom, is not isoelectronic. So for example, magnesium is not isoelectronic. Neutral magnesium is not isoelectronic with neon. It's only its ion that is, right? So neutral magnesium, let's put these back. We have magnesium, 1s2. Then we have 2s2. Remember, the superscripts, the numbers that are floating on top, represent the number of electrons, 2 and 2. The 1 and the 2 up front represent the energy levels of those orbitals. And of course, the letters represent the types of orbitals. 2p, and then we have a total of 6 electrons, so that's 2p6. And then we have 3s, and then we have 2 electrons there. Now, another way to represent this, a shorthand way to write this out would be to recognize the fact that, hey, wait a minute, look at this, 1s to 2s to 2p6, all of this right here is equal to what? Well, it's equal to neon again, isn't it? So what I could do is I could represent this as neon, just this portion though. That doesn't mean I'm finished. That only takes me through 2p6, and then simply write out the rest of the electrons that are not covered by the neon. Neon only takes me up to 2p6. Neon is equivalent to 1s2, 2s2, 2p6. But because I have electrons beyond the 2p6 level, beyond neon, I do have to represent those. But this is a shorthand way. It saves me the trouble of writing all this stuff out. So I could write it this way, and you can do this only with noble gases. This is what's called the noble gas notation. It is only allowed for noble gases. You cannot do this with any other element. Noble gases represent the complete energy level for that row. Noble gas notation. Okay, now let's do magnesium 2+. Let's actually see what it looks like. Magnesium 2+. So that implies that we remove those last two. So that's 1s2, 2s2. Everything's the same at the beginning. 2s2, 2p6. Now you can either write 3s0, or you could simply leave out the 3s0 altogether. It's the same either way. And this, of course, is equivalent to, magnesium 2+ is equivalent to the noble gas notation, neon. Noble gas notation of the ion. This is of the ion. These are not the same thing, right? An ion and a neutral atom are not at all the same thing. I want to make that clear. These two were neutral. These two are charged. Charged particles are not at all the same thing. They are not the same thing as neutral atoms. Anything that has charge in chemistry, the charge becomes the most important feature of that thing. Everything else falls by the wayside. So the noble gas notation is simply neon for the ion. Noble gas notation for the neutral magnesium metal element is neon 3s2 because you have those extra 2 electrons. Those valence electrons in neutral magnesium have not been lost, but in magnesium 2+, those valence electrons have been lost. And that makes a huge difference in the reactivity and the activity and even the physical properties of magnesium. It's like they're not even the same element anymore. They've completely changed. They are the same element, but the difference between an ion and a solid metal is the difference between night and day. So isoelectronic sets. A lot of times you're going to want to identify isoelectronic elements or ions, I should say, with their nearest noble gas so that you can use the noble gas notation to just simplify writing out those ions. Be careful though. Sometimes you have ions that still have d orbital electrons. So they aren't truly, their valence electrons may be gone, but they still have, maybe 10 valence, or it's not 10 valence, but 10 electrons. They're still 10 electrons away from being isoelectronic with their nearest noble gas. We'll take a look at that, some other possible examples where that might come up in the next part of this series here. Likewise with sulfur. So sulfur has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p4. What about sulfide? Sulfide with a 2- would have the electron configuration 1s2, 2s2, 2p6, 3s2, 3p, 4 plus 2 is 6. You'd fill in those last 2 empty spots. Anytime you see 3p6, you are at a noble gas. There's no way to fill up the p subshell without arriving at a noble gas, at least at that point. So this would be equivalent or isoelectronic with what? It would be isoelectronic with the element argon, argon. Argon also has the exact same electron configuration, 1s2, 2s2, 2p, 1s2, 2s2, 2p6. I think I skipped a few steps here. 1s2, 2s2, 2p6, 3s2, 3p. 2 plus 4 is 6. There we go. So argon also has this exact same electron configuration. So a sulfide, this is, by the way, the ion of sulfur is called sulfide. Sulfide ion is isoelectronic with argon, as is chloride, and you should double check that, as is potassium and calcium 2+, potassium ion, monocation, and calcium dication, Ca2+, and chloride monoanion, Cl-1. All of these are isoelectronic with argon and of course with each other. They all have the exact same electron configuration. You might be tempted to think that gallium 3+ is also isoelectronic, but it is not. It is not isoelectronic with argon because once you get rid of the valence electrons of gallium, you're still left with 10 d block electrons, which of course argon does not have. Argon has no d block d orbital electrons, but gallium has 10 of them. So be careful about that. You can lose all your valence electrons from a p block element and appear to have lost all your S&P top energy, highest energy S&P orbital electrons and be back to a noble gas of the prior row. But be careful, if you're in row 4 or lower, also some d block, d orbitals and d orbital electrons, 10 d orbital electrons to think about it, that every p block element in the 4th row and lower also contain those electrons. See if you can find any other positive or negative ions, even if they're not totally realistic. See what else you can do to some of the surrounding elements around sulfur or around calcium or potassium. See what you would have to do to those elements to also make them, to give them charges that would make them isoelectronic with argon. That's a great exercise, and that really will help you, both not with just this, but in the topics that are coming up. Okay, I hope that was all informative. This is, again, part 1 of orbital energy diagrams. We have a few more concepts to look at. For one thing, we've only looked at main group elements. So in part 2, we're going to look at how to treat D block elements, and we're going to look at which the relative energies of the electrons, which electrons are lost first. D block elements are, of course, metals, so they have a tendency to lose electrons. They have no tendency to gain electrons. And we'll look a little bit deeper in the cause of electron spin, paramagnetism, diamagnetism, and 1 or 2 other topics that are specific to the D block elements, to just a few D block elements. So we'll take a look at those. I hope that was all informative. Let me know how it's going, and take care, everyone.